Permission to speak again. The next panel can go ahead and come up while I do the introductions. We're a little behind, but we'll catch up. A couple of interesting things on this is I got to fly the X-59. And in my long and sordid career in a couple of places, I got to fly some simulators and different spacecraft proposed and existing, but I never got to fly an airplane. And last night at the reception, we had an X-59 simulator, which they'd let you pretend to fly, but then also you had to eject from it also. I didn't do the G-loading very well in the ejections. But Dr. Edgar Wagner is the director of the Integrated Aviation Systems Program at the Aeronautics Research Mission Directorate at NASA. So that means he's in charge of those things. A couple of things that I noted on him, and one of the most interesting things I noted on him was he came in as an aerodynamics researcher at Langley, but then he moved over and started running architecture and engineering. And I did a little something like that. I went and worked architecture and engineering as soon as I got out of the shuttle program. And that was a hard transition. Those guys speak differently than what I used to speak, and they have different terminology. Terminology I thought meant one thing, meant something different. And then he moved from the A&E world back into technical aviation and space stuff. So Ed, your panel. And you have a clicker too.
Great, thank you. So first, I just want to thank the AAS, Patrick and Jim, and my colleagues from NASA, Glenn, Janet, Marla, and others, for having the foresight to put together this incredible panel to talk to you about something that, if you don't realize it right now, we think that in the not-too-distant future will certainly affect your life and certainly affect mobility for the citizens of the world. So we've got a pretty terrific panel here. We've got Gene Holloway from Aerion, David Hyde from AIA, Dave Richardson from Lockheed Martin, and Laura Smith-Velasquez from Collins Aerospace. I could give a lot of opening remarks, but we've got a pretty good story, I think, in the way that we have structured the presentations. So we're going to kick this off with David Hyde talking about AIA's Vision 2050 and what they view as a promise for supersonic travel to kind of set the stage here. David's the Director for Environmental Policy at the Aerospace Industries Association. They represent about 350 aerospace companies. He's responsible for developing industry positions relative to environmental impact from aviation, such as emissions and noise, and this includes advocating for smart regulations and environmental standards that enable sustainable growth of civil aviation and promoting new aerospace technologies. Prior to joining AIA, David worked in aviation policy in the UK's Department of Transport. He led several areas related to aviation noise and airspace modernization, and he's had other roles also in the UK relative to national and local governments. He's got a BA in history from the University of Southampton and a Master's of Science in Global Politics from the University of London. So, David?
Thanks, Ed, and good morning, everyone. So as Ed just introduced, I'm with AIA, the Aerospace Industries Association, and we are the leading trade association of the US aerospace and defense industry, representing almost 340 companies, including all of those on the panel today. And we consider ourselves the voice of US aerospace and defense, though sometimes that voice does have a British accent, which can throw people off a bit. So AIA was formed in 1919, and for those of you who can do the math in the room, which is full of engineers, so I'm hoping that's all of you, you'll realize that means AIA turned 100 this year. And for the past 100 years, we've been really proud to serve an industry which has had such a profound impact on our world. But our industry is also a forward-looking one. So to mark our centennial earlier this year, we published our Vision 2050 report. And that really sets the scene for the future aerospace innovations we expect to play a role in shaping our world in the coming decades. And this means, along with completely new concepts such as urban air mobility, which will transform how we move around cities, the return of supersonic transport, and specifically the advent of sustainable supersonic transport, can really revolutionize how we experience our world. So to give a bit of history, I'm not sure if any of you knew, but in the 1930s, it took 6 days to cross the Pacific by plane. And even in the 1940s, a flight from the southern US to the south of South America could take up to 3 or 4 days. But with the dawn of the jet age in the 1950s, we were suddenly able to travel to continents thousands of miles away in just a few hours. And it's that ability to travel faster, which is the reason aviation has become so successful. And without that, none of the advances in aviation becoming the most sustainable or efficient form of transport or the safest form of transport would have happened. So if we can fully realize the potential of supersonic transport, we feel the benefits can be just as great and just transformative as they were at the dawn of the jet age. So I'm going to steal some figures from one of our AIA's member companies who aren't on the stage today. But if an aircraft was able to travel at Mach 2.2, that would mean you could travel from New York to London in just over 3 hours. Or what I think is even more amazing is you can travel from Sydney to California in less than 7. So to put that in some perspective, that means a round trip where you would currently spend 30 hours just in the air. You would be able to travel for a business meeting, have a full day's worth of meetings, and travel back home in about 24 hours. So this can be really revolutionary. So while we think this is a great vision, at AIA we also have a lot of experience, and we know that if this vision is to happen and supersonic travel is to become a reality, that we need to ensure it's done in an environmentally responsible way. And using low boom technology in Mach Cutoff, which I know some of the other panelists are going to speak about in more detail than I possibly ever could, but that's going to help to remove what currently is the biggest barrier to sustainable supersonic flight, the sonic boom. And I was fortunate enough to be at NASA's community noise test in Galveston last year, where they were testing community reactions to a noise that is expected to resemble that produced by the X-59, which I think Ed and Dave will speak more about later. And my experience there was really amazing. So these booms, if we're going to call them those, were barely audible. And that's to a group of people who knew what they were listening for, had monitoring equipment, and knew exactly when they were going to happen. And as I said, we could barely hear those booms when I was there. But we also need to go beyond just low boom technology. So that means we need to ensure that as an industry, we are producing these aircraft with the latest advances in propulsion technology and materials and aerodynamic design capabilities. This will help not just local airport noise, which is a big issue for several communities around airports in the US and globally, but also it will allow aviation as a whole to ensure it can achieve its ambitious climate reduction goals. So we need to ensure that we prioritize fuel efficiency when we're designing these aircraft, and also looking for ways where the supersonic manufacturers can really lead in sustainability for aviation. Could be perhaps championing the use of sustainable aviation fuels, like some of our companies have come out and said they will do. So I'm not sure many of you may be aware that modern subsonic aircraft are 85% more fuel efficient, and 75% quieter than the first generation of jetliners. And at AIA, we believe there's no reason why, with the continued support of NASA and the wider research community, the industry can't deliver equally impressive improvements in supersonic capabilities over time. But what is important is that today we create an environment where this technology can thrive, and we don't stifle this technology at its nascent stage. So at AIA, we're working very closely with the FAA and the International Civil Aviation Authority to put in place measures which safeguard communities and the environment, but give the technology the environment where it can really flourish. And the work NASA is doing on the X-59 is a really important part of this, and industry is also doing work to try and make sure that we can balance that very carefully, the balance between sustainability and flourishing this technology. And we think things are moving in the right direction. Some of you may be aware that just the week before last, the FAA issued a proposal to streamline the application process for testing aircraft at supersonic speeds if it could be shown that there will be no significant environmental impact. And we think this is a really important first step in having that relationship between government and industry to try and get this technology to where we want it to be. And crucially, we think this is the first step towards enabling AIA's Vision 2050 and the benefits that supersonic technology and the other technologies we explore will bring for our society. Thank you.
Thanks, David. So that sort of sets the vision that we're talking about. The reason I'm here, I manage a fairly broad portfolio in NASA aeronautics, but all of it is focused on integrated demonstrations, wherever those need to be, whether it's flight or ground-based. It includes technologies associated with electrified aircraft propulsion, integration of unmanned aircraft into the National Airspace System, urban air mobility, all of stewardship of all of NASA's flight assets, and what one of our huge big programs is, demonstrating the X-59, the low boom flight demonstrator. Over the past few years, NASA sponsored a number of market studies as well as what David alluded to for AIA, and we certainly believe that there's a huge potential relative to new markets for aircraft manufacturers and operators worldwide. And this includes aircraft that will totally change the way that we work and the way that we think about long-distance travel. Vehicles that can travel at speeds that will redefine our workday, making it possible to wake up in the U.S., fly to London or Brussels for a meeting, fly back to the U.S. and sleep in your own bed. But one of the major barriers to achieving this vision is the regulations that are in place worldwide that prohibit supersonic flight over land. This principally is a result of the rather obnoxious sonic boom emitted by the Concorde that flew commercially starting in 1976, and it flew until 2003. Now, researching technologies for commercial supersonic vehicles has been a major thrust of NASA aeronautics for the past couple of decades. And we've made tremendous progress in ground testing, the ability to accurately predict the fluid mechanisms associated with supersonic flows, including shock propagation, flight testing, the associated instrumentation to support flight testing, including the ability to actually observe shock waves from chase aircraft. So in particular, NASA, along with various industry partners, has developed some design guidelines that have the potential to reduce the obnoxious sonic boom associated with the Concorde to something akin to what I like to call distant thunder on a summer night, a rumble that may well be lost in the ambient noise. David talked about this. Not unlike your neighbor closing the trunk in the driveway next door. If you're not listening for it, you may not hear it at all. We've tested these technologies in wind tunnels. We've evaluated them in noise simulators. We've looked at flying special maneuvers using military aircraft. David talked about that in Corpus Christi. And now it's time to gather some validated response data on real people, how they respond in diverse communities, diverse terrain across the U.S., and how they react to the noise generated by well-designed supersonic aircraft. So NASA Aeronautics has embarked on a project to design, build, and test a large-scale, manned, supersonic experimental aircraft, the X-59, the Quiet Supersonic Technology Vehicle, or QUEST. So we're doing this in partnership with Lockheed Martin. We're building a representation of a supersonic commercial vehicle, and we're committed to having the first flight in 2022. But if things go the way that they've gone the last year, we think we may be able to fly even a little earlier than that. This vehicle is almost 100 feet long, 33-foot wingspan. It'll fly at Mach 1.4 at slightly north of 50,000 feet. And we've defined a set of requirements to build this aircraft to, and we've kept that fairly stable through the project. And this is to minimize the adverse effects of what we call requirements creep that so often accommodates large design-build programs like the X-59. So after we prove that the vehicle can be safely flown over a range of its flight envelope, we thoroughly understand the noise signatures that it generates, then we enter a phase that we call community response testing, where we fly regular routes over U.S. communities and gather data from how people respond to these overflights. And this is going to take about 2.5 years to do this. We'll take these data, we'll analyze them, then use them in conjunction with the regulatory community, the FAA in the United States, ICAO and its Committee on Aviation Environmental Policy internationally, to help inform policy and rulemaking associated with supersonic commercial flight over land. So that gives you kind of a brief thumbnail sketch of what NASA's interest and what we're doing relative to the commercial supersonic market, and one of our key major thrusts in supporting knocking down a huge barrier relative to opening up this market. So in conclusion, I want to emphasize that NASA shares the vision of the supersonic community that David talked about, where fast air travel is available to a broad spectrum of the traveling public. This is a future where supersonic aircraft will not only be able to fly over land without creating what the FAA calls an unacceptable situation, but compared to the Concorde, will be able to do this more efficiently, more environmentally responsibly, and more affordably for the traveling public. So I want to thank you for that, and then for our next couple of presentations, we're going to hear from those practitioners, those folks that see the market and are going to actually go forward and build an aircraft. So Gene Holloway from Aerion is the first panelist that represents that phase of the market. Gene actually started with NASA as a co-op student over 45 years ago. He started his career with Northrop Grumman, then he moved to Lockheed Martin, and since 2018 he's been with Aerion, where he's the Chief Sustainability Officer and Executive Vice President for Environment and Sustainability. He's got a lot of responsibility relative to the first boomless cruise system that's going to be flown. I'm really excited to hear about some of the technologies and how they're going about looking at this. Gene and I have an affinity for Auburn University. We're fellow plainsmen. Gene got his BS Air and Aerospace Engineering, as did I, and he has a master's from Pepperdine. So, Gene?
All right. Thanks, Ed. Most people, I think, don't really understand that when the Boeing 707 first entered service back in the early 60s, it doubled the speed that we traveled by air. But since that time frame, we haven't gone any faster. And a lot of times we've actually slowed down just a little bit. So, you know, we've had tremendous leaps in technology in terms of quieting the jets down, making them more fuel efficient, making them less greenhouse gas emissions and the like. But we really haven't done anything to make the jets faster, with the exception, of course, of the Concorde and the short-lived Russian Tu-144 commercial jet. So there hasn't been a supersonic civil transport in the last, new one in the last 50 plus years. So Aerion has identified a commercial market, for supersonic travel, and we believe that this is the appropriate re-entry into that realm of advancing the speed at which we travel commercially. We've taken the steps to go after it from a more or less moderate risk standpoint. We think we got to take not quite baby steps, obviously, but we're looking to have that next step where we're going to almost double the transport speed again. All right, we are designing the world's first supersonic business jet. It'll have a Mach cruise of about 1.4. That's why I say it's roughly almost doubling where we are today. But the challenge is, for us, is really kind of threefold. All right, let's see if the thing works. Yep, that was the wrong way. There we go. So there's three major challenges for us, and one of them is really the biggest one, okay? So obviously we have to address the supersonic issue of sonic booms, all right? We also have to address how do we certify landing and takeoff noise and en route noise in general, that's out there. These are challenges that the world's been building supersonic jets for decades, military supersonic jets for decades, but, luckily I come from a military background. We never had to worry about certifying them to civil standards, so that allowed us to do all that development. The challenge, one of the biggest challenges now is we're going to have to civil certify it. And so that's where the LTO and the en route noise comes in, the whole issue with sonic booms over land and the current ban on traveling supersonically over land. How do we meet the gaseous emissions levels? That one is a tremendous challenge. There's a lot of things being done to reduce gaseous emissions. Unfortunately, the laws of physics says if you're going to burn a hydrocarbon, as your fuel, the faster you go, the more hydrocarbon or the more CO2 you're going to produce. So that's a tremendous hurdle for us to take on. And so along those lines, what really becomes, I think, our biggest challenge is public perception, okay? How do we educate and convince the public that going to supersonic travel in general, whether we do it over land or just over water, is a good thing to do? Because currently right now, our operational plan is that we will fly subsonically at about 0.95 Mach over land, and then once we get out over internet outside of domestic airspaces, we'll accelerate out to the 1.4 and travel supersonically. But we plan on exploiting a technology and a phenomena that's been there, we've known about for the last 6+ decades to ultimately allow us to fly supersonically over land responsibly, so that, as we've already been talking about, the worst that you might hear is some sort of little bit of a rumble in the background, and if you're living anywhere in probably a suburban or urban environment, you probably won't even notice it against the background noise. So with that, I'll start with the first part, which is to talk about Mach cutoff. People who work in the world of sonar, and certainly those who work in the world of RF, are very familiar with, something that's called tunneling, all right? Mach cutoff basically is that same thing. It's just now we're talking about it in the air. It's something, like I said, we've known about since the 50s. We've done a tremendous amount of work, NASA in particular, and along with the FAA, have done a tremendous amount of research into it and understanding the phenomena and the things that trigger it and the like. But it's always been one of those things where you can fly on a standard day, you can fly supersonically slightly, and actually operate the aircraft in a way such that the sonic boom doesn't reach the ground, okay? That sharp edge crack, you'll never hear it. We don't pay a whole lot of attention to that most of the time, certainly when we're building fighter jets and the like, because we're in a hurry to get out there to those higher Mach numbers to go out and exploit the higher speeds. So, and also, of course, we're operating in a region that traditionally has been a very high drag, region for aircraft. But there is rational, good, solid rationale for looking at it from that standpoint of how can I exploit that in a limited fashion that does allow me to increase my speed over land, and then I'll increase it further once I get out over the open water. So in effect, what you're doing is you have the phenomena of Mach cutoff or Mach threshold is the Mach number at which you can fly where you get this focus boom that's just at the ground level, all right? And so if I slow down just a little bit, what happens is I have this caustic layer, and that's the refractive layer in the atmosphere, that begins to come up off the surface of the Earth. And I don't have to slow down very much before I start raising that caustic layer, a few thousand feet off the ground. And so my example here is, if I'm flying at 55,000 feet on a standard day, and I'm looking at sea level, if I look at the threshold Mach that puts the sonic boom on the ground, that's 1.15. If I back off to 1.12, I actually raise this caustic floor 8,000 feet off the ground. All right? So now in that 8,000 feet, we know that the sonic pressure waves, these N waves, will exponentially decay as they approach the ground. That's why you only hear this little tiny bit of a rumble. All right? So our objective is how do we put together a system, operational real-time system on board the aircraft that allows the pilot to pre-plan his flight in a way that he's already setting up his flight plan to fly at Mach numbers that will not put the boom on the ground. How do I then, once I've uploaded that to the aircraft and I go off and go fly, how do I ensure, the general public that I'm not going to, run into any climatic conditions that will create a sonic boom on the ground where it's not intended. So those are kind of the challenges that we face in terms of putting that part of the technology together. From the standpoint of both takeoff noise and the emission side, the engine that we have chosen for our aircraft, we've co-developed with GE Aviation. It's the Affinity Engine. The core of this engine happens to be the same core that powers the B-1 bombers. That's where it started life before it became the CFM56. And now the CFM56, as many of you already know, is the most used jet engine in the world. It's got over 91,000 years worth of flight time on it. So that makes it pretty darn well-known, established, behaviors and the like. And so what we've done is we've gone back and looked at modifying that core, reducing the bypass ratio on it to get better, thrust at supersonic speeds and the like, and applied other advanced technologies to both reduce the emissions as well as the sound coming from it. So that now the combination of those modifications to the engine, the fact that the aircraft is designed to fly supersonically, so the thrust is actually scaled. So the thrust for the aircraft has been sized for cruise, not for takeoff. So at takeoff, we have a tremendous amount of excess thrust. So there are things that we can do operationally in our takeoff profiles that allow us to climb out in a manner that will keep our LTO noise down, we believe, actually below the current stage 5 levels. And so that's what we're working with both through the CAPE and through, from ICAO standpoint and with the FAA to change and create the new rules for supersonic aircraft that allow us to operate it in a manner consistent with the fact that it's a supersonic jet and not a subsonic jet. So we can take advantage of some of those things to be able to realize that performance. The other thing that we're doing from a mission standpoint is that Aerion has committed to being a different kind of OEM, and that from day one, we are going after making our jet the greenest we possibly can, not just from an emissions standpoint, but also from how we manufacture it, the components that go into it, the things that, who our suppliers are, driving those requirements into all those avenues. And the reason why we're doing that is because going back to the whole issue with hydrocarbon fuels, we know we're going to be producing more CO2 than a normal subsonic jet will. We expect to be producing about twice as much at full cruise. How do I counter that? Well, the only way really today that I can do that is I do it by looking at the operation of the jet from a life cycle assessment, not from a tank to tailpipe standpoint where I know I'm going to be putting out more CO2, but rather if I look at it from the total life cycle of well to wake, all right, and that's where the sustainable aviation fuels comes in terms of using fuels that I'm taking advantage of carbon sequestration all the way along the path, and then all the things I can do with the jet. We believe our analysis has shown that we can actually have, from a life cycle standpoint, our jet can be carbon neutral on day one if we're burning, especially if we're burning 100% SPK, or synthetic paraffinic kerosene. So those are the kinds of things that we're trying to do to show that we can be environmentally responsive as a OEM for a supersonic jet as we move forward, and hopefully will be a good example for the rest of the industry as a whole and any of the startups to say this is the way we need to go forward as an aviation industry just in general in order to be more responsive, in order to meet the 2050 goals of reducing carbon by 20% or 50% over the 2005 levels. So with that, the last bit is Aerion doesn't see itself just as being a maker of supersonic jets. We actually see ourselves as a global mobility company, and that, we're looking to help the world move faster and in terms of travel, so that you can take more time to enjoy where you get. But, just in general, the things that we see with this aircraft is, it's the first civil supersonic aircraft in America's history, okay? It's super cruise capable. We believe it's about the second fastest super cruise capable airplane out there currently, behind military jets. Has the longest super cruise legs unrefueled. It's going to meet, the levels for noise that are currently out there subsonically. We're already meeting, most of the subsonic emissions levels. We believe we can actually meet most of those. And it's also going to be the first production jet that will operate, supersonically, or capable of operating supersonically over land at low Mach numbers and not have a sonic boom that reaches the ground. And with that, thank you.
Okay. Gene, thank you very much. Our next speaker is Dave Richardson from Lockheed Martin. We're going to hear a little different way of addressing this market. Dave's going to talk about enablers for quiet supersonic flight, some of the technical requirements, as well as the business case. Dave is a director for Air Vehicles Design Technology for the Skunk Works. He's responsible for leading development and coordination of air vehicle technologies for Lockheed Martin Aeronautics, as well as the low boom flight demonstrator work. He's from Reno, Nevada. He joined Lockheed Martin Advanced Development Programs, the Skunk Works, 28 years ago as a conceptual designer in Burbank. He's moved through increasing responsibilities through his career, from a design lead, air vehicles lead, chief engineer, program manager, and then to his current position. He's worked fighter, transports, bombers, rotary wing, lighter than air, and ISR programs. Dave holds a master's degree in mechanical engineering from Brigham Young. And Dave, take it away.
Thank you. I hope I get this clicker right in terms of going forward and backward. Okay. Ed talked a lot about the X-59 program. We're moving right along with this program to actually have first flight in 2021 and to then turn the keys over to NASA for the testing with the basically the sound testing and community responses in 2022. I hope that most of you have seen this airplane. If this is the first time that you've seen it, you're kind of impressed with how long it is and how skinny it is. When I was first looking at this as we were putting it together, it looked kind of silly because if you look at it from the side view, the landing gear seems to be so far in the back of the airplane. The fineness ratio is the dominant design feature for an effective low-boom airplane, which is the length to the diameter of the airplane. So the skinnier and the longer we can make it, the quieter the boom will be, as we could stretch out those shock waves and manipulate them so that we don't get them all stacking up to be really loud all on top of each other. If you look at it also, the nose is very pointy. I'm going to show you another picture here in just a second of another aircraft. And that making a very sharp pointy nose is important, and Aerion can tell you that too. It also drives an issue that I'll speak about later in terms of integrating radars, other things like that. The other thing you'll notice is that the pilot actually doesn't have a forward-looking There's no windshield. So he's doing it all, the Spirit of St. Louis and Charles Lindbergh. There is some new technology here that NASA's working on, which is the external vision system to help us in certifying this airplane, because we are going to fly it across the country and hopefully fly it, I think, to Europe. And we're gonna need to have some of that avoidance capability and traffic detection. There was a question earlier today about workforce, and I wanted to bring that up with respect to the X-59. In all of industry, we were talking about the propulsion companies earlier, but even within the airframers, it's tough to find good help these days. It's really, really hard, and getting people out of school, we can't get them fast enough. The thing is the question was, well, what can we do with the universities? And even universities, I know, are having a hard time getting people to get into those engineering fields that would go into aerospace rather than into telecommunications or other things. I will say that the Artemis program, the X-59 program, other things like this, for when I was a kid, looking at Apollo and other things, they inspired me. And the X-59 program is very different from other things that we do at the Skunk Works in that it is unclassified. We can let people know what's going on. And everybody's excited about first flight and actually being able to invite their families to come and see this happen. And so when we talk about what sort of things can we do, it's investing in these types of activities that really do inspire those who are younger and see things and they say, I want to do that. So there's a lot of benefit to this program. So some of you may have been at Aviation 2019 last month, where we debuted this concept for an airliner that is a low boom aircraft. Again, it's dominated by that fineness ratio, that really pointy nose, and just this really long, skinny fuselage. For us, we've been looking at supersonic transports, well, back in the day in 1970, but in earnest since about 1990. We were looking at supersonic business jets, and then about 2001 or so, we started looking at quiet supersonic business jets. And we've been working with NASA now for many years in this area. And they've commissioned certain studies on this. Boeing, others are looking at it, Gulfstream. For a low boom, quiet supersonic airplane, it really does lend itself to an airliner where you have a long fuselage and you can stack a lot of people in it. We need that length. You don't sit a lot abreast, but you do have a lot of people sitting one after another longitudinally in the aircraft. This airplane was shown last month by Mike Bonanno, who's our chief engineer on X-59. The main things that I want to take away from here, again, is to notice that there is really no good forward visibility, that there is a sharp, pointy nose that makes it very hard to integrate a radar in. But as far as cost and efficiency, this airplane flies at Mach 1.6 to 1.8. That is effectively twice as fast as what you get today. And above that, you start to have to incorporate variable geometry in the inlet, in the nozzle, and other things having to do with aerodynamic heating, where there's a jump in the cost of the system. Below that jump, you want to go as fast as you can without hitting that jump. So about 1.6, 1.8 is about where we want to go. That's a sweet spot. The other thing that we want is to have a twin-engine airplane. I know that Aerion would kill to have a twin, and you'll see the way industry is going is away from the 747s, the A380s, to large twin-engine aircraft as far as operational cost. Those two engines, you can see on the chart here, they're twin 40,000-pound class engines. They don't exist. The nearest thing that there is to an off-the-shelf engine, actually, we'd have to go to Russia to get some of these things, and I don't think we're going to, even then we'd have to modify them. But they're old engines. The United States and the world was going to faster engines, 50 years ago, 60 years ago, but we've gone to more efficient engines since, and so there's a drive to drive up the compression ratio in the engine so that the temperature going into the combustor, I think we talked about this earlier, the temperature at the turbine inlet is now the temperature at the compressor exit is how far up the temperatures have gone. So the faster you go, actually, the hotter it gets. And we don't have those engines that have those lower compression ratio type engines or compressors anymore. To go on, actually, the main chart that I want to show today are the last two. They're word charts. David and Ed spoke a little bit about this, so did Gene. These are the enablers to quiet supersonic flight. And actually, these are in order. As we've gone and debated these in the halls at the Skunk Works, this is pretty much the order that we see them in. Number one is the regulations. I won't speak to these anymore. We've heard about them. It's not only the boom piece of it during cruise, it's the takeoff and landing, it's emissions. But getting this right is critical, and doing it right, and making sure that the decision makers are well informed as well as public perception are critical. Number two is the engine. You can't have a supersonic transport without an engine. I won't go into all the details of the A, B, C, and D here, but the right thrust class, the right cycle for flying at Mach 1.6 to 1.8, meeting the noise requirements, and then the other thing is ITAR. Developing an engine like this would obviously have applications militarily. And if we're going to put these on an airliner and sell these internationally, it wouldn't take much to take these engines and militarize them, put an augmenter on the back, and have them actually drop into a fighter. So there's ITAR implications with the engine. The development cost also is a significant one, and I will get to that at the very last bullet on this chart. The national and international airspace integration for navigation. If you think about Star Trek and, you see the Starship Enterprise, jump into warp and jump out of warp or drop out of warp, these airplanes are going to have to come out of supersonic flight. They're going to have to go into supersonic flight. And no matter what happens, no matter how we design it, it will create a loud boom. Past that point, we can make it quiet. But at around about 1.2, we will make a loud boom. And then we're going to come down from higher altitudes and integrate in with subsonic aircraft that are coming into these large airports. Where do we put those corridors, or how do we integrate those airplanes so that we can create those booms? Do we have to have them over water? Do we create certain corridors over land? So there's some issues that we do need to consider as we move forward. The market and the business case, I think that the studies over the last several decades actually have shown that this is where the world wants to go. That there are people who are willing to pay these types of airline prices, high net worth individuals who would be willing to buy these types of aircraft. Number five, the ability to design an efficient low boom aircraft. It's here thanks to NASA. This is not something that's out in the future that we need to worry about. I spoke about the artificial forward visibility and how in the world we can get a radar integrated and other situational awareness into the aircraft, given the fact that really looking forward is a hard thing to do. So there's some work there. And again, NASA is leading the way in a lot of those things. And the last one here is funding. And it's the big issue for the engine. The engine probably is, and I'm going to make up a number here, and so the propulsion guys, engine companies here won't squirm, but we're looking at several $1 billion for just the engine. And the airplane is a factor of 2 or 3 on top of that for the total price. So these are large expenditures. I think we talked about it earlier about certifying the little drones that are going around or electric vehicles. It's one thing that people have these technologies, but it's another one to make them safe. It's another one to make them certifiable for passengers to travel in. And to design aircraft like that is no small feat. So the funding is a big thing as we go forward, whether it's done privately or whether it's done publicly. But without an engine, probably we're going to wait until that happens. My last chart really goes to, I guess I don't have my last chart. Oh, why did I come? No. The last chart is entitled, "We Got to Get It Right." And this really goes to Dave's effort with AIA and also some of the things that Gene talked to. There are the decision makers. There is public perception. And there's a desire to hurry and rush into some of these things and to get a lot of these regulations changed, but we need to make sure that we do them correctly. We need to do them in cooperation with NASA and the FAA, and also industry, making sure that we come together. And that's a lot what David's job is, in helping tie us together so that we have a unified voice. But the worry that I personally have, there we go, is if we make a mistake and for some reason public perception is off, or the decision makers don't understand what we're asking for. If somebody comes in and says, oh, no, don't worry about that, we can make that happen, but we really can't, I would really hate for us to miss this opportunity because, and this is just my opinion, I think if we blow it now, we're probably going to end up waiting another couple of decades again until we can do this. And so it's critical that as industry, both on the government side as well as the contractors, that we, and even universities, that we work together and make sure that we have a unified voice and that we're going forward in an informed way. And that's all I got.
Hey, thank you so much. I really appreciate that. So a different perspective, you just heard that. So our final panelist is yet going to talk about something else. So Laura Smith Velasquez is with Collins Aerospace, and she's going to talk about one particular enabling avionics technology to manage boom. She's a human factors and systems engineer at Collins. She has almost 2 decades experience in designing systems for flight deck, air traffic management, unmanned systems. She's a principal investigator on integrating the NASA sonic boom display into the flight deck, developing human-machine interfaces and systems architect for supersonic commercial transports to manage the boom carpet and enable overland flight. In addition to being a systems engineer for this particular, the low boom flight demonstrator, she's also worked on research and technology development for intelligent automation design in both flight deck and unmanned systems, with a focus on human autonomy teaming. Very, very important subject. She's got a Bachelor's of Science in Aeronautics and a Master's of Science from Emory-Riddle. Holds a commercial pilot, small UAS, and aircraft dispatcher certifications, and is one of 100 astronaut candidates for the Mars One program. So, Laura?
Great, thank you, everybody. I'm really excited to start talking about this technology because I think people don't realize how far we've come in technology since Concorde. We've made huge leaps and bounds, not only in materials and engine performance, but even in our processing capability in the avionics in the aircraft. It's incredible for just how much that we've been able to accomplish. So I'm going to talk about a lot of the human factors aspects. Up is down. Interesting. Speaking of human factors. But I'm going to focus. I'm going to focus on some of the research objectives of this project in particular. One of the interesting things is we have supersonic pilots, we have commercial pilots, but we no longer have supersonic commercial pilots. Not only that, in dealing with the domain and the technology space, the way you fly a modern supersonic aircraft will be very, very different from the way you would have flown Concorde. Concorde flew heat temperatures. They had all this issues with aeroelastic friction and all this different type of technology issues. We don't have those today. We've resolved a lot of those issues. And so one of the things first things I had to do is come up with figuring out the concept of operations, not only in the air traffic management realm, which NASA did quite a good study on that, by the way, at Langley, but try and figure out what technology and how it would change the way a pilot would fly an aircraft. But not only that, how to design a flight display so they can manage their boom carpet without being a physicist and have to understand their wave propagation and how to graphically display that so they can understand it really quick and be able to modify their flight plan real time in the cockpit. So managing the aircraft's boom footprint, our goal was to provide the pilot the capability to plan and carry out a flight, okay? But that allows them to reduce the sonic boom, avoid hitting populated areas, so you can actually place your boom. We talked about, okay, you're going to have to make a boom. Well, with this technology, I can actually place it in a particular area. So one of the concepts was, okay, we have these corridors, and maybe you have a standard departure. which encloses a boom area to where you can boom. And so some of these concepts. The other thing is, or inhibit the boom from reaching the ground altogether using the Mach cutoff technology. Okay. The other thing is to enable the pilots to see where their sonic boom will hit, so it's predictive. And how do you do this real-time predictive? So you're not just doing, pre-flight. You have to do in-flight, because one of the major precepts is this is based on forecast weather data. It's a forecast, right? You also have to maneuver for traffic. There's going to be a lot of different types of issues that you might have to slightly maneuver off your original flight plan, and how to do that and make decisions and go back and forth air traffic control and do that very quick. The other thing is display the pilot feedback. We talked about that, but to provide a guidance capability. There's a lot of degrees of freedom in supersonic flight. You have all the flight parameters that affect your boom. You have all the weather parameters that affect your boom. And then you also have the constraints management of what limits are we going to have to follow in order to manage. So all that has to be put into a flight deck to create a pilot decision space, and so that they can really easily manage their flight plan. And then the other aspects that I was doing is developing a notional architecture. How do you get all that weather data into the aircraft? How do you take all this processing power? Because a ray trace actually goes not just from the aircraft technically, it goes above, and you characterize the atmosphere all the way to the ground, and every few seconds you're doing that processing of that wave propagation as it hits the ground. So that's just one ray, and you're doing that every few seconds throughout your entire flight plan, right? Well, we've gotten processing power and improved the NASA algorithm so well that we can do it coast to coast in 10 seconds for an entire flight. This is what I talk about processing capability. It's just amazing. But how do you architect that in the system? So there's all this information and display and data and logic that also happens behind. So we come into, I talked about the concept of operations, but the pilot working groups. So this was very thorough, actually. We have Collins Aerospace Flight Operations. Some of them are test pilots, some of them are just regular corporate pilots. So I used both of them. I also previously talked to Concorde pilots, which were very helpful in understanding wave propagation as they saw it and how they used it in original aircrafts, but then all understanding the gaps, and then working with the NASA Armstrong pilots to do usability testing to do that. So we actually integrated the NASA prediction algorithms with the terrain database. Now here's one of the neat things is I got to build upon some of the earlier research that Collins Aerospace did with NASA to develop synthetic vision systems. And now we develop synthetic vision systems and enhanced vision systems that we also have partnered to put on the low boom flight demonstrator. To look at that aspect of integrating the data and without these forward vision. Okay? And so also enhancing the way to do graphical flight planning and to visualize the terrain interaction with the sonic boom. And actually, I should probably go back. So just so you can see the difference in terrain interaction. So that's actually Death Valley where the blue is, and that's the wave propagation. You see how it's attenuated by the mountains? So the pilot can tell just how far they might have to maneuver. And say the valley was a city. They're like, okay, well, maybe I should go 10 nautical miles to the left, and then our boom doesn't get over the mountains. So you can see the magnitude of your boom. You can see the breadth of your boom. You can understand, there's another, I didn't bring that slide because that's a little difficult and don't have time to explain it. But there's a pilot decision space based on trajectory modeling, not only of the Mach cutoff, but how that affects your flight plan, your Mach number, your altitude, and your lateral maneuver within your flight plan of where to actually put your boom carpet and how to manage that. So going back to this, the other aspect we work on is a weather sensitivity analysis. On the right-hand side, is your standard no-wind atmosphere of what that ray trace for your shot cone, right, looks like. And you'll notice we don't have the full cone on there. It's the nice hyperbola because it goes out into the atmosphere. But there are many, many cases, depending on winds and temperature, where you get secondary booms, or even the primary boom is an over-the-top boom. And when we started doing this weather sensitivity analysis for NASA to really characterize just how the boom wave propagates and how it affects it, one of the things we noticed in doing this 3D visualization of each ray along that entire angle of the shot cone is that we had some very unexplained boom carpet issues. And what we learned is it's actually quite often you'll have a ray trace that goes, or shock trace that goes up, but then it comes back down due to the atmosphere. So also being able to track and characterize that and the conditions of when that happens, how it happens, and to be able to avoid that, and providing a weather monitoring system in the aircraft so that the pilot knows not to go into those conditions or regime, does all that work for them that they don't have to do in flight to manage their sonic boom. Thank you.
Okay, thank you, Laura. We want to be cognizant of the time, so I've got a whole slew of questions that we could start off with, but why don't we start off by asking the audience?
Sure. Yeah, we're using the Conference.io app, and so we've got some upvoted questions here. And the first one is, how well do we understand the impact and shock interactions of multiple aircraft sharing close airspace? Does our research need to answer that question as well?
I mean, the only people who are doing that right now is you, Ed.
Yeah.
And we have no plans of flying in formation with airliners, so.
So, and we've done very little research relative to that because I don't think that that's going to be a major issue as we get started in this marketplace. As the market grows, perhaps that'll be something that, that we'll be addressing. But right now, we just don't see that as one of the key barriers.
If I might also, it's our understanding that DoD actually has done a tremendous amount of research on this going back, decades, and looking at what are the potential destructive effects of a sonic boom overpressure, from whether it be interacting with a nearby aircraft or something on the ground and the like. And as well as answering the question of, okay, so if you're flying over the water and you got this, strong sonic boom, is it going to harm the fish? Okay, and so a lot of those answers actually have been empirically identified, and the answer resoundingly has been that there effectively isn't any, because it takes a tremendous amount of overpressure to actually damage, for example, another aircraft that's, because one of the big issues is, okay, so if I overtake a commercial liner or some guy in his Cessna 152 flying down below me, what's going to happen? And the biggest issue potentially is you might have a startle effect. It's not going to overpressurize. It's not going to drive him into the ground. He's, if there's some sort of a loss of control, it's because he was startled enough that it caused him to do something he shouldn't have done. That's been kind of the main aspect of it. There have been recorded incidences where Concorde has overtaken jetliners en route, and it did just that. It startled the aircrew because they weren't aware they were going to be overtaken. It didn't cause the airplane to be upset. Surprised the people in the back too a little bit, but it's not. That's kind of the limits on what happens.
Great, thank you. And that actually just about answers the next question that was submitted, just about detrimental effects on birds and low-flying other aircraft. So I think we'll move on to the next one. Is the level of investment for R&D for supersonic propulsion commensurate with the challenges that supersonic transportation faces in terms of LTO emissions and noise?
No.
I think that is the answer. I mean, and that is one of the huge long poles.
It's an economic driver. I mean, and there's right now there's not. It requires such a huge investment that there needs to be a giant payoff somewhere. That's why I'm saying that, if we develop these sort of engines, do we do it in conjunction with the government? Because it's a big investment.
I mean, longer term, it really begins to come down to ultimately changing the basic, concept of engines as we know it today. I think, it's not just going over to electric. Because we've got that huge challenge currently that, a gallon of jet fuel is roughly equivalent to 50 pounds worth of battery, okay? And so for an aircraft, we're very weight sensitive. That obviously is a non-starter. So, while ground transportation and surface transportation in general, can much more readily, move towards batteries and the like, because, let's face it, they're held up by the ground, not by, lift. It's going to be a much harder road for aircraft to go down that path.
Okay, and while I ask the next submitted question, if anybody in the audience does have a question, just raise your hand, wave a little bit. We've got a couple of microphones here. So with the need for the X-59 to be long and skinny, how will the current design scale up to a commercial aircraft, which will be much wider to carry passengers with the same low boom signature?
So again, I showed you the picture of that green airplane that we had. If you look at the X-59 and kind of the diameter to fit one guy in it, the cross-section of a guy in a cockpit that's basically like a T-38, the airplane's about 100 feet long. To get about 3 to 4 people, 3 people wide and an aisle in there, the airplane is basically twice as long. It's about 200 feet. And so the point that I made earlier about that is more conducive for an airliner than maybe other applications, business jet, whatever it might be, is imagine taxiing around, or actually imagine running through your house with a broomstick sticking out your nose as you try to, go through doors or get into the refrigerator and things like that. Taxiing around with an airplane that's 200 feet long. There's some logistics there that you need to consider, and the thing is that a business jet is actually wider than passenger jets. I mean, there's a lot more comfort and opulence in it. And so the business jet would need to be 200 feet long. And that's a big airplane. So again, I think it allows itself to an airliner because that length, you can use it when putting a lot of people in it. It's not the most luxurious first class type seating. It is small. If any of you've My wife flew on the Concorde. I didn't get to. She got to. And she hates airplanes. And it was small. That was her comment. She goes, I didn't like it. It was too small. It's a small cross section. But that's how this airliner would be scaled up from the X-59. That was also one of the requirements that NASA gave, is that the airplane had to be big enough that it was representative of the real effects of a larger aircraft. We could have done this with a small airplane, and then we wouldn't have proved anything. So it had to be of a certain size in order to prove, and a certain speed. We also had to get past about Mach 1.3 to make it realistic for something that's an airliner.
All right, I think we might have time for one more. Let's see. Oh, we have one in person, actually. Hang on one second. Excuse me.
Thank you. Do you see infrastructure changes being an issue with the much longer aircraft and having to change airports and things?
Well, probably. I don't think that you're going to see, I don't know. I can't predict the future. I was going to say you can't see thousands of these things at all over the world, but there was an infrastructure change that went in for A380. You're all aware of that. I mean, billions were spent across the world at airports to be able to handle this heavy aircraft, as well as the gating issues that were required. And now you see people saying, well, I don't want any more A380s. This airplane, again, we don't have the picture up, but the actual, if you had a jetway that went down to this airplane, there's almost 100 feet of airplane sticking out in front of where the door is. So you'd have to park farther away from the actual building. So there may be some logistical issues, but as far as the runway, as far as runway length, anything else, no.
And I'm actually going to do one more question from online, because I think it's a pretty cool question. The fly-in at Oshkosh, the AirVenture, is coming up soon. And so the question is, would the X-59 ever make an appearance at an air show to help educate people on what's trying to be done?
From my point of view, that's a great question, and we think it probably would. Don't know about the requirements from a runway point of view at Oshkosh, but I think one of the themes that you heard through this was public acceptance. And part of public acceptance is getting people knowledgeable about what this vehicle would be. And so that's something that we certainly think when we do our community response testing, that there's going to be opportunity for the public to come out to airports, look at that vehicle, see what it is, Who knows? They may be, able to walk up and touch it. But certainly that is a key part of what we, from a NASA point of view, want to do. So we'll be getting hard data that we'll be using, of course, with the regulatory community, but we also want to make sure that the public is familiar, understands what we're doing, why we're doing it, and the closer they can get, then I think the better off that we will all be relative to acceptance.
Well, round of applause for the panel, please. Thank you.